everyone. This is the second part of the 22nd lecture in the series Mathematical Methods for Economics. In the first part, we introduced the concept of the derivative of a function at a particular point, and we introduced it as the slope of the tangent to the curve at the point that we are looking at. So in particular, if you look at the slide here, we define the derivative as f prime of a equal to the limit of f of a plus h minus f of a divided by h as h tends to 0. We also gave a diagrammatic formal interpretation, a geometric interpretation to this particular definition. In particular, we drew a distinction between what is an average rate of change as against an instantaneous rate of change. So what we have here, the limit is the limit of this expression is the instantaneous rate of change or the derivative. And here we are basically emphasizing the idea of an infinitesimal step. That is what the concept of the derivative is based on. What is happening for a very, very small change, teeny-weeny small change, infinitesimal small change in x. What happens to the variable y? And the instantaneous rate of change is different from the average rate of change, which we define as f of a plus h minus f of a divided by h. So let us now look at some problems which help us understand how to calculate the derivative with the help of this definition, the limit of the difference quotient. We'll be developing rules to calculate the derivative in the next lecture. But for now, let's practice using this limit definition, because this is also something that is very useful in various analysis. So look at this example 1, which asks you to use the definition of the derivative at a point, which is f prime of a equal to the limit of f prime of a plus h minus f of a divided by h as h tends to 0. So it's asking you to compute f prime of a when f of x is equal to x squared. Now, f prime of a is by definition limit of f of a plus h minus f of a. Now, f of a plus h is nothing but a plus h the whole squared, right? And f of a is nothing but a squared. So in the numerator, we have a plus h the whole squared minus a squared divided by h. This, when we open the brackets in the numerator, becomes a squared plus h squared plus 2 times a times h minus a squared. And you can see here that the terms a squared will get cancelled. And we now get the limit of, after cancellation of a squared, we get the limit of h squared plus 2 times a times h divided by h. Here we can take h common, and once we do that, the h in the numerator will cancel out the h in the denominator, so that when I apply the limit to the expression h plus 2 times a, because h tends to 0, the first term will vanish and I'll be left with 2 times a. So this is the derivative of the function at the point a, the function x squared at the point a. Now, what we'll do is, just to, because there are several formulas, there are several versions of this limit formula that are used in various textbooks. So let me just walk you through at least 2 of these formulas, and let's use these formulas for the same calculation that we've just done, which is to calculate the derivative of the function f of x at the point a. Now, notice here that our definition of the derivative is limit of f of a plus h minus f of a divided by h as h tends to 0. Now, because here we're talking of a specific point a, we have put a here in brackets. But if I bring in the symbol x, which can denote any value, then that is also another way of writing the formula for f prime of x. So f prime at x then becomes the limit of f of x plus h minus f of x divided by h. And here you can, if you want to calculate the value of the derivative at point A, then you can simply put x equal to a, and you're going to get exactly the same formula as the one above. So in general, I can write the formula for the derivative as a limit of f of x plus h minus f of x divided by h. So in this sense, when I look at the function f of x equal to x squared, my derivative, which I had earlier calculated as 2a, is now going to be written as f prime at x being equal to 2 times x. It's just a general way of writing things. And then if I want to calculate f prime at the point A, then I can simply put x equal to a. There's yet another version of this formula that is very often used in textbooks. So this is something which you might want to familiarize yourself with. What we have done here is that in this formula, we have put x equal to a plus h. Okay, so if I put x equal to a plus h, then this part, this term in the numerator will become f of x. Then the second term will be minus f of a. Now note here, because x is equal to a plus h, simple algebra will tell you that h is equal to x minus a. If I take a to the left hand side, so h is equal to x minus a. That is why in the denominator, instead of h, I have written x minus a. Basically, we are now writing things in terms of x and a rather than h. And the other thing to notice is that because we want h to tend to 0 in the original formula for the derivative, here h tending to 0 is the same thing as saying that x tends to a, because x is equal to a plus h. So if h tends to 0, then x will tend to a. So my formula now becomes, the formula for the derivative now becomes f prime at a is equal to the limit of f of x minus f of a divided by x minus a as x tends to a. So this is also a formula that works very nicely in many the problems that you do. So let's apply it to this particular function here, where we were calculating the derivative of the function at the point A. Our function here is f of x equal to x squared. So we have defined f prime at a as the limit of f of x minus f of a divided by x minus a as x tends to a. Okay. Now f of x is what? F of x is x squared. I'm just substituting for these terms. F of a is a squared. So I have the limit of x squared minus a squared divided by x minus a. Now x squared minus a squared can be written as x minus a into x plus a. So we can easily cancel out the x minus a in the numerator and the denominator to get the limit as x tends to a of x plus a. And that is nothing but, because as x tends to a, we're going to get this x going towards a. So in the limit, this will become 2 times a, which is exactly the same answer that we got from the original formula. So these are just different variations that you should be comfortable with. You should be able to apply different the variants of the formula, the original formula, in whichever way you find it comfortable. Now, in continuation to this example that we were talking about, let me, because we have talked of the derivative as a slope of the tangent to the derivative at a point A as a slope of the tangent to the curve at the point A. So let's now bring in a question which brings in the flavor of that concept. So here the question is asking you to find the equation of the tangent to the graph of f of x equal to x squared at x equal to 1/3. So the point is 1/3. Now, you all know that because the tangent line is a straight line, and the straight line, the equation for the straight line is given by, let's suppose we have the slope point form. So, the equation would be given by y minus y1 is equal to the slope times the slope of the line times x minus x1, right? Now, what is our x point here? So, the equation, let me just show it to you on the slide here. So, the equation of the tangent will then be, because our point that is given to us is a comma f of a, the equation will then become y minus f of a, so that's your y1 here, f of a, equal to the slope of the tangent line. Now, what is the slope of the tangent line? That is the idea that we have just developed. That is nothing but our derivative at the point A. So, the slope is nothing but f prime at A, and that will then be multiplied by x minus x1. So, here our x point is A, so x minus A. Okay. Now, A here is 1/3, so we can easily calculate, because I want my value of the function at x equal to 1/3. So, f of A is going to be x squared, so that's going to be 1/3 squared, that's nothing but 1 by 9. And we've already calculated f prime at A, which is twice A, so that's going to be, because A is 1/3, that's going to be 2 by 3. Okay, so we just substitute now. We have all the required information to write down the equation of the tangent. So that that's going to be given by y minus f of a, which is 1 by 9, equal to this slope 2/3 times x minus 1/3, right? And this can be simplified to get y equal to 2/3 times x minus 1 by 9. Okay. Now, what I'm going to do is, because we use derivatives a lot in economics, I'm going to walk you through an application which relates to the total cost function that we use in economics. Basically, the total cost function, it tells you the total cost of producing Q units of a commodity. Let's suppose we are producing, let's say, t-shirts here. So, C of Q is our total cost function. C represents the total cost and Q represents a number of units of the commodity. And let's suppose our starting point is A, so we are producing Q naught units. So, the associated cost is C of Q naught. And let's suppose we increase our production to Q naught plus H, okay. So, that then leads us to, that then can be used, that information can be used to calculate the average rate of change, which is nothing but C of Q naught plus H, because your cost is going to increase to C of Q naught plus H minus C of Q naught, okay, divided by H. So, that's nothing but the slope of the secant AB. This then gives us the average rate of change, which tells us how the cost changes as the quantity produced increases from Q naught to Q naught plus H. Now, what we can do is, we can, so by the way, this, if you notice here, this is also nothing but the ratio BM divided by AM, that is your average rate of change. And this then we can develop this further to develop the idea of the instantaneous rate of change, which will be nothing but the limit as H tends to 0 of this particular difference quotient. But let's first talk of the average rate of change, and one very common application that we have in the cost function, which is something which you've probably been doing from school, is that we often take H equal to 1. So, this is what we call the average analysis and the average concept, and here we are asking ourselves, what is the additional cost of producing one more unit of the commodity? So, just to back up, so I've defined the average rate of change as C of Q plus H. If I, instead of taking Q naught, I just take Q as the original point, C of Q plus H minus C of Q divided by H. So, suppose I'm interested in understanding what is the additional cost of producing one more unit of the commodity. That is where I can take H equal to 1, right? And my formula will become, the average rate of change will become C of q plus 1 minus C of q. Now, this is something which we call the incremental cost. So, you've been doing this calculation for the incremental cost in your microeconomics course in school, I'm sure, which is basically where you must have calculated the additional cost of producing one more unit of the commodity. Now, in economics, we are also concerned with what is known as the marginal analysis, what is happening at the margin. And that leads us to what is known as, it's a very important concept in microeconomics, it is known as the marginal cost. The marginal cost it's basically nothing but the derivative of the cost function with respect to Q. And this is where we're answering the question, what is the additional cost? What is the increase in cost if I increase the output produced at the margin by an infinitesimally small amount? So, if I increase the output produced at the margin by an infinitesimally small amount, by a very small amount, then what is the increase in the total cost? That is what is called the marginal cost. Here we are talking of what happens, what is increase in total cost at the margin. When I increase Q by an infinitesimally small amount, by a very teeny weeny small amount. So, unlike what you do in school, what you do in school is actually what is incremental, what it's called incremental cost, and marginal cost is actually the first derivative. It is the first derivative of the cost function with respect to Q, and that is the limit as limit of C of Q plus H minus C of Q divided by H as H tends to 0. So, let me walk you through an example to show you the incremental steps and how we can compare the average rate of change with the instantaneous rate of change. So, what we'll do is we'll make the incremental steps smaller and smaller. So, let's suppose we have a cost function given by C of Q equal to Q squared plus 3Q plus 100. This question asks you to find the average rate of increase in cost as Q increases from Q naught equal to 1 to a quantity, let's say 2. So, here you can see that my incremental step is the change in quantity is basically 1, or what happens to the average rate of increase in cost when Q1 is 1.5 or 1.1 or 1.0001. So, the first part of the question asks you what happens to the cost when quantity increases from 1 to 2, okay, by 1 unit. Then the second part of the question asks you what happens to the cost when quantity increases from 1 to 1.5, then 1 to 1.1. So, I'm making the incremental steps smaller and smaller. And what we're going to see here is, and this is what we were showing in the diagram earlier, where the subsequent secants they tend to the tangent. So, we're going to show here that the average rate of change for smaller increments in the quantity, that tends to the instantaneous rate of change. So, let's see how that happens. What the question is asking you to do is, for each incremental step, there are 4 of these specified here, find the average rate of increase and then also calculate the instantaneous rate of increase in the cost at Q equal to 1, and then compare the instantaneous rate of increase, which is the marginal cost, with the average rates. Now, the average rate of change, which is basically it's averaging out the increase in cost over the increase from Q naught to Q1. So, the average rate of change in cost is given by C of Q1 minus C of Q naught divided by H. Q1 is nothing but Q naught plus H. Okay, so I've substituted that here, C of Q naught plus H minus C of Q naught divided by H. So, let's first look at what happens when the initial output produced is 1 unit. We're talking t-shirts here, so let's say 1 t-shirt. Then the new output is 2 units. So, what is the increase, the average rate of increase in cost? Here, the increment is 1 unit. Okay, so C of Q naught is C of 1, and that when we substitute in the cost function, we get 1 plus 3 plus 100, that's 104. okay? So that's C of Q naught. The average rate of change is C of Q naught plus H minus C of Q naught. So C of Q naught plus H is nothing but C of 2, the cost, total cost associated with producing 2 t-shirts. So C of 2 minus C of 1 divided by 1, okay? C of 2, if you notice here, is nothing but 2 squared plus 6 from the cost function plus 100. So that's going to be 110. And that then gives us the average rate of change as 110. That's your the value of the new cost, minus 104, okay? The cost of producing 1 unit divided by 1, because H is 1 here. So that then gives you 6. This is what we call the incremental cost. This is what you would be calculating in school. What is the additional cost of producing 1 more unit of the output? But here, from now onwards, we're going to call it the incremental cost. That's actually the average rate of change. So incremental cost is a more accurate term. Now let's make the step a little smaller. So let's suppose we increase output, and let's suppose we have a perfectly divisible output. So actually t-shirts may not be the great example here. So let's suppose we increase output from 1 to 1.5. Okay, so here the difference is 0.5, H is 0.5. And C of Q naught plus H would be C of 1.5, subtract off C of 1 from here, and excuse me, you would have a 0.5 here in the denominator. Now C of 1.5 is nothing but 2.25, because 1.5 squared is 2.25, plus 3 times 1.5, that's 4.5, plus 100, and that gives you 106.75. So the average rate of change here is 106.75, the final total cost value, minus 104 divided by 0.5, because H is 0.5 here. That then gives you the value 5.5. So you can see here that the average rate of change has actually gone down. Let's think of, let's talk of the average rate of change when Q1 is 1.1. So here, again, we have that C of Q naught is 104. I'm sorry, this mistake seems to be getting carried over to the subsequent slide. So H here has changed. It's now 0.1. And you have C of 1.1 minus C of 1, right? Divided by 0.1. So that's going to be that is, so the last step is absolutely correct. It's just this intermediate step where it was probably a problem of cut, copy, paste. So 104.51 is the total cost at Q equal to 1.1, right? Minus 104 divided by 0.1. So that's 0.51 divided by 0.1, which is 5.1. So it's gotten even smaller. And the last case is where we've taken the increment in output from 1 to 1.0001, where H is 0.0001. So here we have absolutely the correct formula. C of 1.0001 minus C of 1 divided by 0.0001. Now, C of 1.0001 is this particular number here. I haven't shown the detailed calculations because then that becomes too long, but it's simple algebra. You can just substitute the value into the cost function and calculate this. And then this gives us the average rate of change as 5.0001. This is as far as the average rates of change calculations are concerned. Now let's look at the instantaneous rate of increase, or the marginal cost. The marginal cost is given by limit of C of Q plus H minus C of Q divided by H as H tends to 0. Now C of Q plus H is going to be nothing but Q plus H the whole squared plus 3 times Q plus H plus 100. Subtract C of Q from there. So that's what we're subtracting of, Q squared minus 3Q minus 100. And when we open up the brackets, we get 1 by H, Q squared plus H squared plus 2 times Q times H plus 3Q plus 3H plus 100 minus Q squared minus 3Q minus 100. And here you can see the terms Q squared here and here will get cancelled. Your 3Q q will also get cancelled and 100 will get cancelled, so that what you're left with now is a limit of h squared plus 2 times q times h plus 3 times h divided by h, and one of the h terms here will get cancelled, right? So what you'll be left with here is, you can see, if I take h common in the numerator, I'll be left with h plus 2 times q plus 3 divided by h. The h will get cancelled in both the numerator and the denominator, and once I take the limit as h tends to 0, I'm going to get 2 times q plus 3, which is then the marginal cost. Okay, so marginal cost when we at the point q equal to 1 is nothing but 5, because that was our original level of production. Okay, so we have done quite a few calculations here, and now let's just summarize all the calculations that we have done. So we calculated the average rate of change when we started from the production level 1 unit to make it 2 units or 1.5. So it's 1 to 2 or 1 to 1.5, 1 to 1.1 or 1 to 1.0001. So we were making the incremental steps in each case smaller and smaller. And you can clearly see, if you just compare things to the marginal cost here, so you can see that the average rate of change, as your change in Q becomes smaller and smaller, the average rate of change, it becomes closer and closer to the instantaneous rate of change. And that is exactly what we were showing in the diagram in the first part of the lecture, where we showed you subsequent secants, the slopes of which were reflecting this only, the average rate of change. And when the secant approached the tangent line, the slope of the secant as h tended to 0, then that gave us the instantaneous rate of increase, the rate of increase at that instant, so to speak. So with this, we end the second part of the lecture. That's all we have for today. And there's still lots more to come. But until then, thank you very much.